This is lecture 18. And so far, we have spent a fair amount of time talking about the diode. So I think we spent about 2 weeks on that. And we saw the basic operation and also a few applications. And I hope that the idea of a device that has a somewhat of a sophisticated IV characteristics that allowed us to do a wide variety of things. It had this nonlinear behavior. We used it to do all sorts of things like rectification and regulation, but also other functionalities. We built some logic gates with it. So I hope the idea of a device that can allow you to do many things sparked some interest. And so we are going to continue along those lines, but with some new components. And the things that we have left for the rest of the term are the transistors and op-amps. Now, the transistor is a component very much like the diode in that it's made of a couple of pieces of material stuck together, some semiconductors. And in fact, some parts of a transistor, you can look at them and they look like a diode in their structure. So they are very closely related to diodes. The op-amp, or operational amplifier, on the other hand, is actually a circuit. So you buy it in a small package, but if you open it up, inside the op-amp, there are many components, mostly transistors, but also other things. And so it's actually a circuit. However, from the outside point of view, it has a relatively simple structure. And again, it's a component that gives you an enormous amount of flexibility and ability to design and implement different functionalities. So we are going to talk about the op-amp first, and then leave a little more time toward the end for transistors, because there I think we would need to spend a little more time. And so I'd like to go through the op-amps so that we make sure we cover them before we open up the transistor chapter. Although you might say that the op-amp is a bigger component than the transistor. And so going from diode to transistor and to op-amp might be considered a more natural progression. But on the other hand, I think that the diversity that the op-amp brings also to what you can do also gives us insight as to what we might want to do later on with transistors. So I think it's good to talk about the op-amp first. And that's what we are going to start today. OK, so with that in mind, with that long intro, this is our topic, the operational amplifier. Yes. I'll first introduce the main features of the op-amp. I'll draw the diagram. And then we'll see it in action in some circuits. And again, I want to remind you that if you understand the way the op-amp itself works as a component, then with everything else that you have learned about circuits so far, you should be able to solve any circuit that has op-amps in it. OK, so I'd like you guys for you to think about that every time we look at an example, because we are not introducing new knowledge of circuits here. We are only introducing a new component. The only thing that changes compared to what we've been doing for the past 2 months is your element relationships now are the relationships describing an op-amp rather than a resistor or a capacitor. Okay? Nothing else changes in terms of the approach to analyzing circuits. All right. So I'll introduce the op-amp. And let's do that by using its schematic first. It's not a diode. It involves a triangle, but it's not a diode. And primarily, or of primary importance in the op-amp are 3 terminals, actually three nodes, not 2. So this would be one. This would be another. It has 2 input terminals on the left-hand side and 1 output terminal on the right-hand side. So let's label these. And you will see on an op-amp diagram that the 2 inputs are marked as one with a negative sign and one with a positive sign. The one with the negative sign is called the inverting input for obvious reasons, or for reasons that will become obvious more later, but it has a negative sign on it, so you could make a connection. So let's call this the inverting input. And the other one is called the non-inverting input. So let's give names to the voltages appearing at the inputs. So this one, for instance, you can call it, let's say, V2 and V1, like this. Okay. And these voltages, these are node voltages that I'm showing with respect to some reference node, let's say ground, that you have here in your circuit. Okay. And then you have the output voltage, Vout. This is of primary importance in that these are the three pins when you take an opamp, little opamp box package. These are the three pins that you're really trying to use. Now, there's other things, and so I'll maybe mark these with a different color. And in particular, what you would call the supply voltages. So let's call this V supply positive and V supply negative. The reason you have supply voltage is that this is a circuit that needs to be powered on to function. The same way that any of the instruments that you have in the lab, so let's say if you're using your DC voltage source or oscilloscope, you have to plug them in, right, before they do anything. They're a circuit. They need to be powered up. The op-amp is also a circuit that needs to be powered up before you can use it. And these are the supply voltages that you apply to those pins. So let's say for a typical op-amp, maybe the supply voltages will be plus 15 volts and minus 15 volts with respect to ground being at 0. So you turn on the op-amp by making these connections. And for the most part, when you're using the op-amp in doing something within the circuit, you're not very actively thinking about the fact that you have plugged it in and turned it on. The same way that when you represent a voltage source, you're not thinking about the fact that maybe it's plugged into the wall, right? So very often in a circuit, you might see the op-amp without these shown explicitly, okay? But it is very important to remember that they do exist. Because if not, you might run into apparent violation of KCL, for instance, because there is current going through those. They actually exist, right? We might just not show them explicitly. Okay, so I'll just make a note of that. The supply voltages may often not be shown explicitly. But what really matters is the two inputs and the output, and the relationship between the two inputs and the output. And the relationship is simple. The relationship is V out, which is the node voltage measured here at the output with respect to the ground, is a multiple of the difference between the two inputs. So if you take V2 minus V1, whatever you have there, that difference, if you multiply it by some factor, it gives you V out. And this factor for a given op-amp is very, very large. It could be hundreds of thousands, millions, depending on the op-amp. Okay? So that's the primary function of the op-amp. Looks at the voltage difference between its two inputs and gives you an output that's proportional to that with a very high gain. That's what it does. Now, I'll maybe give you a little more detail as to what's going on inside the op-amp. So I'll draw a bigger triangle. And inside it's basically, this is one way to think about it. So this was my V1 going in. So this is the negative input. And this is the positive input. And you can think of them having this, let's call this Ri, as an input resistance. Okay? And then the output is like this. I should have drawn it a little bigger, maybe. This is it. So if I tell you that inside the box, this is what you have. Let me make it nicer. If this is what you have inside the box, in a sense, we are done. We've covered the topic of op-amps at a basic scientific level, you might say. Okay? Because it's a circuit that at a very basic level, you can model with two resistors and a voltage source, a dependent voltage source. You see? That dependent voltage source takes the difference between the two input nodes, so the voltage of the non-inverting minus the voltage of the inverting node, multiplies it by a very large factor, A, and simply applies it here. And then there is an output resistance. And then on the way out, you see that pin Vout. And so if I put this in any circuit, you should be able to solve the circuit with this. Okay? And I'm not exaggerating here. That's what I mean. And it's important for you to think that way. Okay? Because I don't want you to let yourself panic about op-amps. Oh, some new component, something weird, right? It really, this is how you think about it. So let me just write down that we call this Ri, input resistance, Rout, output resistance, and A is the gain. More specifically, it's called the open loop gain. For reasons that we'll talk about briefly in this course, this is called the open loop gain. But what matters primarily at this point is that it's called a gain. It's a gain. So it's a very, very large number, a large value. And it's a dimensionless because it's a ratio of two voltages. It's a voltage-controlled voltage source. So like I said, this is enough for you to be able to solve op-amp circuits. But something to keep in mind here is this, that this holds true, this model. Now, this is obviously a simplified model. And one of the main conditions for it to be valid, and the primary condition that we are concerned with here, is, can anyone suggest what a condition might be that is required for something like this to work? For this model to be applicable? Something that has to do with what we had up here. Yeah, so this works as long as your Vout is less than the limits of your power supplies that are powering this op-amp up. So this Vout is not going to be more than your V supply. So if you're biasing your op-amp with a 15-volt supply, you're not going to get a 200-volt output out of it. And in fact, it is going to be valid up to slightly less than your supply voltages. So let's say if your supply voltages are plus and minus 15 volts, this model is going to work as long as your Vout stays maybe between plus and minus 13, 14 volts. It doesn't get too close to the out. And that has to do with the limitations of the circuit that implements this. Notice I'm not showing the actual op-amp circuit, right? I'm just showing how you can model it. This is a model. This is not the actual circuit inside the op-amp. Okay?
So how are those supply voltages in the top diagram related to these components?
So the question is how those supply voltages are related to these components. And the answer is they are not directly related to this. If you want to see where those supply voltages connect, you have to look at the full op-amp circuit. You see? And that op-amp circuit might have 20 components. And you will see where everything is connected. This is not the op-amp circuit, but this is a model that represents the function of the op-amp. Okay? And so that's a very good question, and it's important to keep in mind that this is a model that, at least for our purposes, is applicable if it's within this range of validity, which is Vout can't get too close to the supply voltages. So, for example, if, let's say, V supply plus is 15 volts and V supply minus is minus 15 volts, then this model works for, say, as long as Vout is maybe between minus 13 volts and plus 13 volts. And this is a rough region. It's not like things are going to completely fall apart as soon as you hit 13 volts. This is where things start to go wrong. Now, what do you think happens if I try to drive Vout to these limits and beyond? So if I'm saying that Vout is modeled by a large gain multiplying the difference between the two inputs, then I can just increase the difference between the two inputs and keep increasing Vout in either direction, positive or negative, right? So imagine, and let's assume that my gain is 1,000,000 for simplicity, right? Then if the difference between V2 and V1 is 1 microvolt, the output is going to be 1 volt, right? Now if I increase the positive input to 10 microvolts, and let's say the negative is at 0, then my output voltage is going to be 10 volts. And if I increase the input difference to 13 microvolts, the output is going to be 13 volts. What happens to the output if I increase the input voltage difference to 20 microvolts? The output will stay more or less the same. It will not keep going beyond that 13 or 13 and a half. And again, it's not going to be straight flat at 13, right? It's going to gradually saturate. So the output, in other words, what we are saying diagrammatically is if you call, let's call the input difference, if you call VD as being the difference between the two inputs, then if you plot Vout as a function of this difference, you're going to see this very high gain linear region is supposed to be a straight line. But then if, let's say this is my V supply plus, and this is V supply minus, the output is going to saturate to a value close to those. Okay? So the transfer characteristics look like this. And this is a pretty high slope. For instance, in the example I just discussed, this slope was 1,000,000. Right? So the axes don't have the same scale here. And it's worth pointing out here a very large value. Okay. This is that range where things are more or less linear, right? This is that. The linear region of this curve. And these other regions, these are called saturation. So this model here is valid if you are in the linear region. Okay. So the criterion for the validity is to be in the linear region. Beyond that, the model changes. And beyond that, the model is easy. The output is almost the supply voltage, either on the positive or on the negative side. The output is a constant value. So as you can see, in the, like in the case of the diode where you had different regions of the IV characteristics, you have to, for a given problem, you have to make sure, for instance, if you're designing something, that the device stays in the region that you want it to be in, or if you're analyzing something, well, trying to figure out which region it is in. Okay. So now it's become really complete. Well, I shouldn't say complete, but relatively speaking, for the degree to which we will get into op-amps in this course at a basic level. Now you can really take this and put it in a circuit and solve for things. Now, I'll ask for you guys to think about a couple of things. For a good op-amp, like I said, the gain A has to be a very large value. That's its basic function. It's amplification. If an amplifier doesn't have a high gain, you may not call it an amplifier. But I have a question for you guys, and maybe this is good for clickers. Do we want a high input resistance? This is Ri, input resistance. Do we want a high input resistance or a low input resistance? You can't necessarily tell that from looking at this diagram, but in fact, it has to do with the way you use this. It's a component that you're, let's say, in a very basic conceptual, at a basic conceptual level, what you're trying to do is take a small voltage that you have somewhere and amplify it. And we all use amplifiers all the time for various purposes. So if you have a small voltage difference somewhere, let's say something that you have picked up with an antenna, and now you want to connect this op-amp to the nodes where you have that voltage difference, well, you don't want this op-amp to influence that voltage difference, right? You don't want it to influence what's going on before you have connected something to it. So you want a high resistance here so that the current that's drawn through this is little. And the circuit, whatever you're connecting this to is not going to change its behavior. Think about, for instance, a voltmeter, right, that you connect between 2 points and you measure the voltage. This is in essence what you're doing, but you're multiplying the voltage with some factor. Well, for a voltage, you wanted a very, very high input resistance, right? In fact, for an ideal voltage, you wanted an infinite input resistance so that there is no current going through the voltage. Sorry, for a voltmeter. Did I say voltage? For a voltmeter, you need an infinite input resistance. Same here. The function of the input is just to look at what's going on between those points. It's not intended to influence them. It's just looking at them and then giving a multiple of them at the output. What do you think we want for the output resistance, R out? A high value or a low value? We want a low value for the output resistance, and here's why. Well, this dependent voltage source gives you the multiple of the input voltage difference here at the node right here. Okay? The output voltage, if you connect your output to something else, there's going to be a current that goes through, right? And depending on the resistance of that other thing, you will have a voltage division between that resistance and this R out. And so if you have a large R out, it will take a big chunk of this A times V2 minus V1. That's not what you want. You want to get all of it at the output, or most of it anyway, right? So you want a small output resistance. For what we would call an ideal op-amp, what are the properties that we want? What is the ideal case of a very large input resistance? Open circuit, infinitely large, right? So R in infinitely large, R out zero, as small as possible, 0. And the gain, perhaps most importantly, how much? Infinity. Now, keep in mind, even an ideal op-amp that you have in a circuit, it still has some supply voltages, right? So these would work as long as you are within the limits in the linear region, right? So then it looks like this. Because there is no output resistance, V out is directly A times V2 minus V1. Now, if A is infinity, what is V out? If A is infinity, what is V out? Infinity. As long as there is a difference between V2 and V1, if you multiply that by infinity, V out will be infinity, which means your output is going to be saturated to either the positive supply or the negative supply voltage. If V2 minus V1 is a positive number, even a tiny positive number, your output is going to be saturated to the plus side. If V2 minus V out, if V2 minus V1 is even a tiny negative number, then the output is going to want to be minus infinity, but we know that as soon as you reach the supply voltage, it will saturate to that. Unless you make absolutely sure that there is no voltage difference on the input, your output will be saturated. Not very exciting. Now, there are cases where you might want to do something like that. You might say this is an excellent comparator, for instance, right? It compares the two inputs. If one of them is slightly higher than the other, it will saturate the output one way or the other. And you will know if V1 is higher or V2, depending on which way the output saturates, okay? So you might say that's a functionality, but that's nice. But there are many, many other things that you can do with the op-amp if you manage to stay in the linear region. And so in many, many circuits that we will see in the next couple of hours, examples that we'll do, you make circuits that make sure that the op-amp stays within the linear region so that it doesn't saturate. Okay? In fact, this is perhaps a key beauty of the op-amp in that what you do with the op-amp typically only uses the quality that it has a very high gain. But it doesn't care much about what the gain is exactly and what the variations may be with the temperature exactly and all that, because the primary function just relies on having a very high gain. The rest of the job is done by everything else that you connect to the circuit, and we'll see examples of that in a minute. But so coming back to this point, if I want to, if I somehow manage to keep the op-amp in the linear region, where Vout is not infinity, okay? It's somewhere between the two supply voltages. If A is infinity, what does that tell me about V2 minus V1? Trust your math. If Vout is a finite number and A is infinity, what does that say about V2 minus V1? 0. Yeah. So, and that's what, in most cases, that's what the op-amp does for you. In most circuits that you will deal with, all the op-amp does is take two nodes there and make sure there is no voltage difference between them. Now, that might sound very weird because it sounds as though I'm doing something that I shouldn't. I'm enforcing something. So we'll see it in action. But let me write this down before we forget, and then we'll see it in action and see what it means. So this is very often how you build a circuit. This is how you build amplifiers and a whole host of other functionalities. You put some components around op-amps to create a circuit that will ensure the op-amp will stay within the linear region of its operation. And then the analysis of the circuit will become very simple too, because, well, V2 minus V1 is 0. Now I want to just show you some examples of what this can do, because maybe this looks a little senseless to say, well, and especially if you look at that, given that there is no apparent connection in this model from the output to the input, how do I make sure that something makes the input voltage difference 0 just because of what the output wants? That will come from what the external circuitry does around it. Okay. Anything that you guys would like to discuss a little more here before we look at some examples? I think, and I hope things will make sense once we go through some important examples. But still, if there's something that you'd like to discuss at this stage. By the way, there's more. There are other pins here. So if you do your lab, in the final lab, we'll have an exercise with an op-amp. And so you have an op-amp in your kits. You can take a look. It has more than 3 pins or even 5 pins. There's a couple of other things. And those have to do with essentially adjusting for non-idealities. And depending on how much time we have, we might talk a little bit about that. But as far as the basic functionalities are concerned, this is the key. Now, at this point, I have the choice of either, subsequently labeling things as a few different sections or chapters, or I can just call them examples. I'd rather call them examples, because what I want you guys to see is not to sort of memorize any of these, but see how we analyze them. And of course, they're important enough that you're supposed to practice them a few times and feel them and know how to do them and how to implement them and all that. But they are really examples. And let's start with this. Assume this is an ideal op-amp. And by the way, if I don't specify, I mean an ideal op-amp. OK? And let's call this R1. R sub F. So in this example, find the ratio of the output to the input node voltages. Try it on your own. And assume that the op-amp is within its linear operation. I think maybe this is also a good time to take a break. So if you guys would like to take a break or keep discussing. Let's take a look at this. Now, I could go around the circuit and set up all my KVLs and KCLs. I could even show all the connections that are implied, maybe because I have maybe connected something else to the input. Let's say something like this. Presumably, this is what I had in mind. But I haven't shown it explicitly. Or you might say, this is what I was thinking. Same thing. I haven't shown it explicitly. So I've just said that node voltage, we have managed to make it equal to V in. And given that we have more experience with circuits, I'd like to do this faster as much as I can based on things that we know. So if we are going to assume that this is within its linear mode of operation, it's not saturated, and if it's an ideal op-amp, what does that say for the voltage right here? What's that node voltage? 0. And why is that? Let's start where we know things, right? So this one we know is 0. This is my reference. ground, 0 volts. If this is an ideal op-amp, and if things are in the linear mode, immediately I'll know that this is also at 0 volts. So I found that node voltage. What about the currents? How much current is going through this? What is the current going through here? If this is an ideal op-amp, 0 amps. How much current is going through here? Also 0 amps. Infinite input resistance. So it's starting to look like a very boring element, 0, 0, 0, 0. Okay? Well, what else do we have? Let's see. What can I say now? What is this current? Let's call this I. What is I? V in minus 0 divided by R. How about this current? IF. What is IF? So by KCL at that node, I minus IF minus 0 is 0. So IF is I is Vn by R. And finally, if I look at the output node Vout and the resistor RF, I have this 0 minus Vout is RF IF. So Vout is minus RF Vn by R, or the ratio that I was interested in, Vout by Vn is minus RF by R. The output voltage has a very nice relationship with the input voltage. It's a scaled version with a negative sign. And the ratio is the ratio of those resistors, RF and R. What happened here? So I took this element that does this very boring thing of imposing a bunch of zeros at the input, and I made a circuit which gives me a very nicely defined gain as the ratio of two resistors with a negative sign. But that's fine. So if you wanted an amplifier that has a gain of 100, all you have to do is to put an RF of 100, let's say kilo ohms, and an R of 100 of 1 kilo ohm, and you will get that gain. So this is an amplifier, and because it gives you a negative ratio of output over input, it's called an inverting amplifier. So this is a very, very well-known op-amp circuit. Do you need to memorize this? No. Do you need to be able to draw it in your sleep with closed eyes and everything? Yes. So it's it should come with practice. So how does this work? This is actually how it works. What you're looking at here is this. The negative node here is held at the ground potential, not by being physically connected to ground, but there is what you would call a virtual connection there. So it's a virtual ground. So the input sees something extremely simple. The input doesn't see the whole circuit. The input simply sees this resistor R. And it gives you a current I that's simply V in over R. And because there is no current being drawn through the op-amp, that current is forced through this other resistor, which then leads to a drop across that resistor proportional to RF. And the difference between the output and ground is determined by that RF. So the input generates that current, I, which has to do with R, and the output generates the voltage Vout, which has to do with now multiplying that current by RF. So this is really the path of how things are happening. The current is going like this, and you get that output voltage drop. Now imagine I have not connected this output to anything else. I have left it open like that. Where does that current go? Where does the current IF go? It has to go back into the op-amp. There's no other place, right? Now, if you look at the op-amp, what I have inside this box, there is zero current going in from the left side and zero current. And then there is some finite current going in from the right-hand side. So what happened? Am I violating KCL? Is the op-amp getting charged up? Is building up charge over time? Had better not do that, right? So where does this current go? It's that thing, right? And that thing, of course, itself was not the full circuit. It was just a representation, right? And in fact, in the actual circuit, ultimately, these will circle back to the supply voltages. And so, in fact, you will see that depending on what you connect at the output of the op-amp, you might be delivering more power to what you have at the output than you have given it input power from your input signal. That extra power comes from the supply voltage, the supply sources. Okay? And so the op-amp is an active element. You would call this an active element. It's something that you have turned on, that it can actually add power to your circuit. So let me draw another circuit and see what we can say about that. How about this? Is this doing exactly the same thing as the previous circuit or something different? I've kept everything the same except that I have flipped the two inputs. I put the positive one at the top, negative one at the bottom. So how about this? This is something very interesting and worthwhile to think about. So I'll ask that you guys think about this on your own at home a little bit before we talk about it. Okay? So does this do the same thing as the previous circuit? Or is there any difference? Okay, so we saw the inverting amplifier. Now I'd like to show a non-inverting amplifier, something that will give you a gain, a positive gain, determined by resistors connected to the op-amp. Maybe this is one thing that comes to mind if I connect things to the positive input instead of the negative input. But I'll let you think about that on your own before we talk about it. But let me draw a circuit that does the non-inverting amplification function. Take a moment and solve this on your own. What is V out over V in? We had a good question here, and makes me think maybe we should remind ourselves of the model for the ideal op-amp. Well, the model for the op-amp here, right? And the voltage difference at the input dropped across the input resistance, right? In the ideal op-amp, the input resistance is infinity. And that's why the input current is 0. These are open circuits. Okay? The fact that the input voltage is 0 in the ideal op-amp is a consequence of the infinite gain. Okay. So the reason the input current is 0 is not that the input voltage is 0. Is because the reason the input voltage is, the reason the input current is 0 is that the input resistance is infinity. So open circuit. Does that clarify? Let's now, it's, I think, good that we reviewed that. Now let's look at what's happening here. So I have the starting point down here where I know that the input voltage Vin has been applied. And if this op-amp has been made, if the circuit has been made such that the op-amp stays within its linear region of operation, then there is no difference between the two input voltages. So I will have a Vin translated here on this node. And it's important to keep in mind the order in which I'm doing these things, right? So I started from this Vin that has been applied and deduced from that there is Vin appearing on the negative side. I also know from the op-amp that this current is 0, like what we just said. And this one is also 0. Now we'll do the same thing that we did last time. So I have a current I here, IF here. And by KCL, that I and IF are the same thing. Now what is I? I is 0 minus Vin divided by R. That's simply minus Vin by R. IF is the same as I. And Vout is Vin minus RFIF. Which makes it that. The ratio then is simply again determined by the values of those two resistors. And as you can see, in this case, the ratio is a positive number. It's 1 plus the ratio of the resistances. And it's a positive number. And maybe this is an easier way to think about it. Maybe instead of the directions of currents that I have shown, you can think about it like this. That Vin having imposed on this node, if Vin was a positive value, it would send the current down this way, right? But that's the same current that's being pulled through this resistor, which will make Vout that much larger. So Vin over Vout is a voltage divider, basically, right? Vin over Vout is simply R divided by R plus RF. So that's one way to think about it. But I'll keep what I had there, because I want to emphasize that you don't need to know how a particular op-amp circuit is supposed to behave ahead of time. You can just choose whatever conventions you want for currents and voltages and solve the circuit. Okay. So this is a non-inverting amplifier. But indeed, you can think of it as a voltage division having been implemented between Vout and Vin. If you think of that voltage division, right? That's the same result, written upside down. I have a question then. Why do I bother with an op-amp? Why not simply do this? What is the op-amp doing here for me? If I could just use two resistors and a voltage divider like this and get the same thing at the output, why am I bothering with the op-amp? Think about this also. An important question. But what I'd like to do is to go through a few other examples of just famous examples that are things that you use the amplifier for, the op-amp for. And by the way, these are real things that you can make, and you will see a problem in your lab where you actually make an amplifier like this. Say again, which node voltage?
The blue point.
Oh, question here. Why do I know that the blue the blue node there is at Vin? And the answer is, when I start the solution, I don't know. What are the steps of solving this problem? What are the things that I do know? I know that the voltage here is Vin. That's all I know, right? But then the next thing I do is to look at what the op-amp does. The op-amp is an ideal op-amp, okay? And we said that for now, let's assume it's operating in the linear regime. So it has a gain of infinity, and the output is a finite value. That will require that the two inputs have to have zero difference between in their voltages. That will be imposed by the circuit, which means then if this input is at Vin, the other one must be at Vin also. So I concluded that from the operation of the op-amp. Another important example. What is V out, or the ratio of V out over V in? Now you should be able to solve this in 5 seconds. Maybe the name of the circuit suggests something to you. Well, let's solve it. If this is V in, this node will have to be V in. And, well, that's all the same node. So what's the use of this? I take a voltage and I create the same things. It's not very creative. Yes. Absolutely. You would also call it a buffer. It provides isolation. Whatever you connect here, this V in. Now let's remember what you have in the back of your mind. This is what you have, right? Something like this. And that might come from any number of things. Maybe this is the output of a small, tiny circuit that cannot provide a lot of current. And it will be very happy to be connected here because the input of the op-amp does not require any current. So there is no load imposed on whatever this circuit is here, be it a small source or an antenna or what have you. It could be a small voltage that you're trying to measure somewhere. So you're not influencing whatever is here because there is zero current going through. On the other hand, you will now get an isolated version of this at the output. And whatever current is required for whatever else is going to be connected here will be provided by the op-amp, as long as it is within the capability of the op-amp to provide that. Of course, you can't expect a tiny chip to give you maybe 100 amps, right? So it will, of course, have to be within the specifications of the op-amp, which you obtain from the manufacturer. But this is voltage follower or a unity gain amplifier, you might say. It's an amplifier with the gain of 1 or a buffer. And it's an extremely important function because it provides isolation. Or let's say it gives you an isolated version of V in. So doesn't impose any current on whatever is generating V in. I want to do a few other important examples. What does this do? So if you know V in, find V out. Let's solve it in the same way. This is 0 volts, that's ground. So I'll have 0 volts also here on this node. And there is no current going through here. So I have 0 amps. So if this is I, the same current is going to go through here, right? I is simply V in over R, because the other side is 0, held at ground. What is V out? Well, if this is the capacitor voltage, I know that I is C dVc by dt. So I can then integrate I assume that the capacitor was initially uncharged. It doesn't matter. I put assuming the capacitor to be initially uncharged. So what does this tell me then? And VC is simply 0 minus V out. And instead of I will put V in over R, and so I'll bring R out. The circuit is called an integrator. The output voltage is, with some ratio, is the integral of the input voltage. And please go verify that I haven't made a mistake. And notice again that you are trying to build a circuit that does something. So typically you're designing something and you have some degrees of freedom over the choice of the values of these resistances and capacitances. And so you can create things with the scales that you want. By the way, if you are bothered by this negative sign, so if you wanted V out to be positive, this integral, is there something you can do very quickly by adding something to the circuit to change this? How about I take another inverting amplifier with a gain of -1, so RF and R being equal here, and I just stack it after that. Now you see you can start building things that look nice. And quickly you can end up with a large number of op-amps. Now imagine, by the way, that you build a few functionalities like this with op-amps, but then you want to make the whole thing into an integrated circuit. So instead of actually buying op-amps to put on a breadboard, you'll say, no, I will just include the circuitry of the op-amps on my chip. So all of a sudden, let's say you had designed something that had 5 op-amps in it. Now you replace each of those op-amps with their circuitry that might have 20, 30, 50 transistors, and you lay it out on a chip. Pretty soon you can end up with a chip with a sizable number of electronic devices that if someone looks at under a microscope, no one will be able to tell unless they start drawing it out and going through all the steps and analyzing. And then they'll be like, oh, it's just an integrator with a simple -1 gain afterward. Right? And this is how electronic design works. That's how you end up with a processor that has billions of transistors. Okay, it's very hierarchical. Well, we have 5 minutes. Can you guys think about making a differentiator? Take a minute, draw a differentiator, and then I'll draw it. Differentiator. If I have 0 on the non-inverting input, I'll also end up with 0 here. And as before, I have 0 amps going in. And this current I will find its way by KCL here. So this is my VC, which is the same as Vin, right? So whatever signal you have at the input, at the output you will get a signal that's the derivative of that, time derivative with some scaling factor. Now imagine if you can make a differentiator and an integrator. So you're doing calculus with these. And if you are doing scaling, and in fact, I guess, well, I'll maybe draw a quick circuit here. What does this do? Take a look at home and we'll talk about it next time. But how about this? Let's call this V1, R1. What does this do? Try this at home. Well, I'll tell you the answer. This is an adder, a summing amplifier. With some ratios, it will give you a scaled version of V1 and V2 added at the output. But try it at home and we'll do together. Oh, this is meant to be plus, not zero. So if you can add things and scale things and invert things and take differentials and integrals, then you can implement differential equations. You can model many phenomena by building circuits that will implement differential operations, differential equations. So this is very, very, the implications here are very, very profound. Okay? Good place to stop for today. Thank you.